Welcome back, folks. So I've asked you to, on your own, go ahead and verify that this is the general solution to the corresponding this homogeneous equation here, and you'll need to actually verify that the solutions are linear independent by looking at the Wronskian. So please go ahead and complete this if you haven't. So now what we want to look at is, once we've determined, and remember you have to determine the trial solution or the homogeneous solution before you can come up with your trial solutions for the method of undetermined coefficients. Let's go ahead and do some practice here. So here we've got this non-homogeneous ODE. The corresponding homogeneous ODE has this general solution. And so the guess is, what should our trial solution be? So our guess for the trial solution, because this function here on the right-hand side is a cubic, our guess is that y sub p should be some sort of cubic function. Now remember, though, that what you need to take into account is also we'll be taking derivatives of our y sub p, and so that means that squared functions, t squareds, could show up. That means that t's could show up. That also means that constant terms could show up as I take successive derivatives of my trial solution. And so we need to make sure those all work out just so. And so the method of undetermined coefficients says what we're going to do is we're going to take as a trial solution at cubed plus bt squared plus ct plus d. That's what we'll use as our guess. Now, the key thing to make sure of is that these solutions, these all clear the corresponding homogeneous solution. And that's what we're going to get to in these subsequent examples. In this case, our non-homogeneous term, the f of t here, the non-homogeneous forcing function, if we think about this as a spring problem, but it doesn't have to be a spring problem, but the non-homogeneous function is t squared cosine 3t. So what we want to make sure of is that when we go to take a guess for this, that our guess takes into account not only the expression that remains after we plug in our general solution and do some cleaning up, but also all potential derivatives that could have showed up in the process. And so if I think about taking the derivative of t squared cosine 3t, there's a few other functions that could show up. For example, when I go to take the derivative of this and I do the product rule, I'll get a linear function the first time I do the product rule for one of the two factors, but I'll also get a sine function when I go to take that. And if I take even more derivatives, we will also get some linear terms that show up. So our guess for the trial solution is that y sub p should look like at squared plus bt plus c times the cosine of 3t. Notice that, I didn't take the time to distribute these, and I could have, but notice that as I take successive derivatives of t squared cosine 3t, it's possible for there to be a t squared cosine 3t, but there are also, as I take derivatives of the expression, it's possible for a b of t cosine 3t to show up, or even a constant after I take two derivatives of that, a constant times cosine 3t could show up. But also, as I'm taking successive derivatives of this by the product rule, I could get a quadratic term times a sine function. So I need to take that into account. So I would have dt squared times a sine function. And just to save room with the writing, I'll factor the sine function out because all of these terms are going to have that sine of 3t. I could also have an et, phone home, sine of 3t. And finally, I could have just a constant times the sine of 3t. So notice that this guess solution takes into account, this is why the method of method of undetermined coefficients works. It takes into account all potential derivatives that could ever show up as we take derivatives of t squared cosine 3t. That also gives a hint as to why I can't use the method of variation parameters for functions that get messier and introduce more and more terms or factors as I take derivatives. For example, this would not work for the function 1 over x. It would not work for the natural log of x or the secant of x. It only works for functions whose derivatives that are products of functions whose derivatives either eventually go to 0 or eventually repeat themselves. Here we're asked to give the trial solution for this, and our guess at what y sub p should be would be ae to the 4t plus be to the 7t. And I'm going to do this now for this problem, and I should have done it for the previous one. I need to verify that none of my solutions show up in the homogeneous solution. And notice that although I'll get some e to powers, e to expressions of t, I'll never get, when I take derivatives of e to the minus 3t, I'm never going to get a e to the 4t. So this does not show up in the homogeneous solution. Neither does e to the 7t. Likewise, I should have verified, although I didn't, that none of these terms in these trial solution guesses show up over here. Here, let's do another one. This one's a little bit trickier. My guess for y sub p, you would think maybe is enough to just say ae to the 4t squared. That certainly does clear all these homogeneous solutions. But look, when I start to take derivatives of this function, when I go to take a derivative, I'm going to introduce through the chain rule a factor of 2t. And then as I take a derivative again, I'll get a factor of t squared out here. So let's just check this. If you were to take d dt of let's just do e to the 4t squared, what I'm trying to point out is that this would give me actually it would be 8t, 8t e to the 4t squared is what that derivative would be. I'll put that up here. But if I were to take the derivative of this, notice I'd have a product rule, and eventually at some point I'll take the derivative of this term. And when I take the derivative of this, or I should say factor, when I take the derivative of this factor right here, I'll introduce another power of t down here. And so actually, the method of undetermined coefficients does not apply. Okay. So hopefully this kind of gets to the heart of some of the, I don't know, I wouldn't call these easy questions, but ones where we don't have to worry. Notice in every case, none of these solutions interfered with the homogeneous family of solutions, and so we were good to go with these guesses. Okay. Again, what we're always doing here is we're always checking to make sure that the guess at the particular solution, all particular forms of that guess, clear the homogeneous family of solutions. So let's get to this key example here. Normally, what would we guess when we have this structure here for a particular solution? Normally, our y sub p would be something like ae to the minus 3t plus, and we got to think about all derivatives that could show up, so we'd have bt plus c e to the 2t. The problem is that when I look at this term of a trial solution that I got because of this component that showed up in the non-homogeneous function, it is no different from what I've currently got in my homogeneous solution. And so this would not help me sort of avoid, because remember this, when I plug functions of this form into the ODE, I don't get factors of e to the minus 3t remaining. I just get 0 because this is the homogeneous solution. So this will not cut it, because these are actually solutions that are found in the homogeneous family of solutions. This will not cut it as a guess. So the trick is to go ahead and multiply by enough factors of t to make sure that we clear the homogeneous solution. And so we get that y sub p would be equal to ae to the minus 3t, and then I'll just write times t here. Now notice that when I do this, this gives me an at e to the minus 3t. That shows up nowhere in my homogeneous family of solutions. Likewise, here, when I think about this solution right here, this part, bt e to the 2t, does not show up in my homogeneous family of solutions. However, that bt e to the 2t came from trying to give a guess at the solution for this factor right here, and part of its guess, specifically the ce to the 2t, shows up right here in my homogeneous family of solutions. So again, what I need to do is multiply this by a factor of t. Now notice this will give me a bt squared e to the 2t. That actually wasn't a problem because the bt e to the 2t already cleared the homogeneous family of solutions. But we still have to follow this procedure. What wasn't clearing the homogeneous family of solutions was the ce to the 2t, but now that I've multiplied by this extra factor of t here, we'd have ct e to the 2t, and we're clearing the homogeneous family of solutions. Folks, I hope this helped. We'll get one more try on this in a video on the next page, but hopefully this gave some clarity as to what we guess as our trial solutions. On the next page, I'm going to ask you to go ahead and find the homogeneous solution to this, and I guess you're looking at my work right here. I meant to cover that up. But on the next video, start with that, and then I will see you as we try the different trial solutions. Thanks for your patience.